Catts question. Now, the Catts question was proposed by Ivor Catts in the 1980s. Ivor Catts was an electrical engineer, and what he brought into question was, where do the negative electrons come from when you send a current through a circuit? In other words, as the current goes down one way, as you can see in these diagrams here that he drew, you have to have a return flow. And if the current hasn't gone all the way through the circuit yet, where does the return flow come from at the same time that the current is going out? Well, why does this become such an issue is that in his proposing this problem and some of the answers that he gave for it, he felt that he was being censored from scientific journals. He was not being allowed to publish in those journals because he was controversial to the accepted thought. So we're not going to get into the politics of that, or whether that really happened or not, because that's a long story by itself. But what we do want to talk about is the basic problems. What we're going to try to cover today is looking at this problem and see if we can explain what's really going on in there using some of the concepts from the ocean universe theory. So let's go to the board here, and we'll see what we can come up with. Okay, so if we draw on the board the diagrams that we have there, we have a power supply, a battery. We're going to run it through a circuit, and we're going to come down through some type of resistor. It could be a light bulb or whatever. It's a plain resistor, and we're going to come back to the battery. Now, the concept is that if this is the plus side of the battery, this is the negative side of the battery, that the current's going to flow this way. It's going to come down through the resistor and return back to the battery. Alright? Well, this is what we call, first of all, conventional flow. Alright? We know now that this is not really the way that the electricity flows. We know that actually the electricity doesn't flow from positive to minus. It actually flows from minus to positive. Okay, so electrical currents flow this way, not this way. All right, so this is what we call conventional flow. This is what we call actual flow. All right, but because all of this was designed around in the 1800s, and this is what they thought the flow was, the way it was flowing, the conventions have been established, and pretty much we keep it that way. But in electronics and physics, we often go to the actual flow because in some cases it actually makes a difference, especially when we're dealing with transistors and things like that, integrated circuits that can actually make a difference. All right, but for right now, we're going to stay with the diagrams. We're going to stay consistent with the diagrams that we saw earlier. Now, this being the case, this is often described, this wire. Okay, now I just want to show what we would have if we were physically to lay this out. The situation we're talking about is we had some kind of battery here, and we have a wire, and say it goes to a light bulb here, comes back, and then this wire is inside some kind of conduit. Okay, so the concept is that we have two parallel wires, and that way there we can talk about collapsing fields around these two, building and collapsing fields around these two wires. That's where it would come into play. All right, and these are kind of thought of as the minus. This is thought of as the minus wire. All right. Now, this is really good as long as we have this situation right here. Now we have, that's accurate. When we do this and we connect these two, this symbology is somewhat ambiguous. And the reason for it is this: if we draw a line in here and break this circuit, we would have to call this positive, because the potential difference between here and here would exist. All right. If we were to break the wire back here, we would have to call that positive. Likewise, if we were to break the wire up here, we would have to call this negative, right? So it's kind of an arbitrary, once the circuit is closed, it's kind of arbitrary where you're calling positive and negative, because this is connected to the negative side. All right. So the problem lies in when the current starts to flow this way down this wire, okay, as you have the current start to flow, you get a field form, right, is the argument. But at the same time, we know there's a field forming here. Well, if the current started flowing this way here, let's close this back up again. How could this, it hasn't gotten to this point yet, so how could this simultaneously have a field develop around it? And that's what where the question arises. So if we're looking down at the conduit, at the wires inside the conduit, our conduit is here, then you can see you'd have this argument here. But how could this happen if the electrons haven't reached down here? So where are these electrons coming from? So we're going to try to explain this situation using a metaphor approach, an analogy. And in our analogy, what we're going to use is that of fluid dynamics. Now remember, what a lot of times we forget is that electrical circuitry, and the way we describe circuits and most of the functions within a circuit, is based on hydrostatics and hydrodynamics, not fluid dynamics. So we're looking at this kind of like it was pipes with fluid flowing through it, and that's how we come to the electrical side. That's why we call it a current, because it's like a current. The term current is taken from water, plumbing, so to speak, the current of water flowing. So let's use that to that. And what we're going to do is we're going to recreate this using a pneumatical diagram, which is pneumatics is air power. And we're going to have our container, and this is going to be our battery. And this is going to be our pressure side of the container, and this is going to be our vacuum side. So in here we're going to have a pressure, and here we're going to have a vacuum. Okay? Over here, for our resistor, we're going to have some kind of little impeller device that is going to bleed off some of the energy from the flow when we get there. So this wire here is going to be represented by a pipe that comes out, goes down into our resistive device, okay, then comes out of there, comes over into our vacuum side. So this is pressure in here, and this is vacuum down here. So this is our plus, if you will, and this is our minus. Alright? So now we have a similar situation here. Now, in this case, in the diagram that is presented by Catts, we don't show any switching activity here. Okay? So what we're going to do is we're going to put in here a valve. I'm going to put the valve actually right here off the side of the device. And let's put another valve right here. Okay, so we can either have the valve open or closed. Okay, we're going to make it closed. Take red out. Make sure our valve is closed. Okay? So, right now, this system, we're going to say is, we're going to call it A, this is the ambient now our two systems. In this case, the switch is open. Okay. Well, if the switch is open here, then this is not positive, and this is not negative, and there is no current flow. Okay. So now our two systems are identical. Now, if the pressure inside this tube, then we're going to call it the ambient air. We opened the tube up and we just connected it up so it's got the ambient air pressure of the atmosphere on it. What would be the electrical equivalent inside the circuit? Well, at this point, got too many cups here. Okay. At this point here, the electrical charge in the circuit would be the ambient charge of the environment around it. So we could actually call this an A also. And A here just means it's the ambient pressure. So the electric density in here at this moment in time would be consistent with what's in the fields around the wire that exist naturally. Okay, so if we were to connect this up, and what I want to do here for a second, let's put another switch in here right at the resistor. We'll see why we're doing this. It makes it a little bit easier to explain what's going on. Okay, so let's put a switch in there, and that would be the same as let's put a valve right here. Close that valve off, and put a valve right here, and we're going to close that valve off. Okay? So now that we have the valves closed, right? Once we connect this pipe up to the pressure side, and we open the valve, okay, we're just going to have it open and close. We're going to partially. Okay? The pressure inside this pipe within just a short time period, this all becomes pressurized. And it becomes equal from this valve all the way back to here to pressure inside this container here, inside our pressure container. Same thing would happen if we close this valve, close that switch, and the moment we close that switch, this wire becomes positively charged. Okay, there's no current flowing through it, but it's still positively charged. It takes a, just like this would. What would happen is there would be a surge that would come down here, and it would fill that pipe with the same pressure as here. Okay, so now if we do the same thing down here, we open the valve, and now we have a vacuum. Any ambient air that was in here becomes rushed back in this way instantly. This is going this way. Okay? And this whole system becomes at the same charge, with the same vacuum level. Same thing would happen up here in our electrical diagram if we close the switch. Okay, so now this is all equally positively charged. This is all equally negative charged, all the ways up here to this other switch. Now we have these valves closed. So here's the state of this system when we're talking about, just if I can draw it over here, this little battery that we drew earlier, right? When the wires are here, and we haven't hooked up the little light bulb or whatever our resistance load is, we haven't hooked that up yet. This wire is positively charged, and it's negatively charged. It's just as positively charged here as it is here. Just like the pressure in here is the same pressure as right there. So we've got positive charge, but we don't have any real flow yet. Nothing's flowing. There was that onrush when you connect it up, just like when we connect these wires up, there's an onrush. All right, so now if we open this valve here, okay, really swing around a little bit one way or the other, depending on how that is designed. And that will become equally pressurized inside there. It's the same thing when we close this valve. This resistor now becomes positively charged. Okay? Still, there's no current flowing through the system. Okay? So now, we're going to open this valve down here. We open that valve down there, and we immediately have flow coming this way as the pressure tries to fill in this vacuum coming along here. Okay? And so we're going to now have created flow. This no longer is really a vacuum because it's got pressure in it. And this is no longer really a pressure because it's flowing. So you have flow going, but this right here does not equal this, and this right here does not equal this, because this is higher than that. This is a lower pressure. It's moving outwards and it's coming around. It's not at a vacuum anymore because it's got pressure coming through it. It's got the gases coming through into the vacuum, and this is spinning and it's just acting like a resistor and slowing down that amount of volume or pressure that you have going through there. It's really the volume will be the same. It's just how fast the pressure that is coming through. It's like similar to the voltage up here. Okay, so the same thing happens when we close this switch. Once we close this switch, this wire here is at the same charge as this wire here. So this wire here is no longer positive, no more than this wire here can be called negative. Okay? Now, there is a pressure differential. Okay? This is P and this is P prime between these two. Okay? Just like there were a voltage, P equals V in this case, so you know, you can call it voltage. Just like there's a pressure differential between P here and P1, between these 2 points, because of the resistor. You got a resistor here, you got a resistor here. So you're lowering the potential, you're creating a potential difference because you have less pressure here. Now that's going to stay like that, okay, until this chamber equals this chamber. Okay, so when let me change this to N for normalized. Okay, so when these two chambers are at equal pressure, this is no longer a vacuum and this is no longer pressurized. They're at equal pressure. Okay. At that point, you're going to have a stop and flow here. Okay? At that point, the pressure differential between these 2 points will go away. Because the pressure down here is equal to the pressure up here. The resistor isn't going to stop that. What happens up here in an electrical circuit is the same thing. There is going to be a differential between these 2 wires, a voltage differential, as long as this battery is live. Okay? But at some point, this battery is going to go dead. And when it's a dead battery, okay, and let's say this, theoretically, let's just theoretically say we can reach a zero state where the battery is totally dead. There is no potential difference between the 2 terminals, okay? For the sake of our discussion, that's kind of hard to actually reach in the real world, but for the sake of our discussion, let's just state that. At that point, there's not going to be any voltage differential between here and here. This is going to be both P. Okay? There's not the voltage in here and the voltage on this side of the resistor are going to be equal. The resistor is going to become in a mute point at that point. So there's not going to be any voltage flow in here. The point point that I'm trying to make here, that's the most significant, is the fallacy of the argument to begin with. Okay? Because as soon as you connect the wires to this battery, each wire almost instantaneous, for the short distances we're talking, it's instantaneous. I mean, if we want to start talking fractions of nanoseconds, there is a time lag in there, and we can say that in 1 nanosecond or 1/10 of a nanosecond, 1 foot, and we can say that we can actually calculate that and measure it with our modern computers, but a few years ago couldn't. But once that charge takes place, it's already there. As soon as you connect that, as soon as we can make this connection, and let's see, get this pen right here. My fingers messed it up. So close these valves, which is the same as closing this valve here. So we take the resistor out, okay, this immediately becomes positively charged. And this immediately becomes negatively charged. Okay, so this is a vacuum. This is, the equivalent of a vacuum, an analogy equivalent of a vacuum. This is pressurized. This is the analogy equivalent of being pressurized. The moment it's connected, the moment this valve is open, those two are at the same pressure. So we really don't have the situation that is being discussed in the problem, because when we connect this resistor in, this is already negatively charged. Okay? So if we're using the conventional directional flow, which is this way, all right, what we're saying is this has already got electrons in it. Okay? So this is where we're looking at it from an actual electron flow diagram might be a little bit more helpful, because what we're saying is the electrons came down here and filled this up, okay, and then this way here was empty, but it was totally empty, just like this was totally empty. So there is no vacuum flow at this point. It's already there. The charges, this charge is just like these two. The charges have already been established. Your flow point begins right here, not back from here, when you connect the resistor in, just like when we open these valves. Okay? So this is a problem sometimes with arguments, is that they create a fallacy argument. And in this particular case, the answer is really that the moment you connected the wire, the negative charge was already throughout the whole wire. The positive charge was already throughout the whole wire. So there is no movement of the negative charge down the negative side of the wire when the flow is connected on the positive side. And how did that happen? It happened when they connected the wires. Okay, so if the last thing you connect is this resistor, then the only flow at that point, it starts right here. And that resistor fills up. And then these charges are already in place. So an example of how a fallacy like this can occur, and it seems so logical on the surface, is we're going to take a look at what a simple mathematical fallacy. So I'm going to erase this. I'm going to give you an example of a mathematical fallacy that defies logic. I kind of wrote it down. I tend to forget this problem. I don't use it much, but let's say we have a problem, a mathematical problem, A equals B. Okay? And what I'm going to show, what I'm going to prove to you is that this cannot be true, or if it is true, that 2 equals 1. Okay? So let's just do some mathematical operations. If we multiply both sides of this equation by A, right? And we could have used B, but we're using A. We'd have A squared equals, let's turn this around, AB. Okay? So, now, if we subtract a squared from both sides, right, we can have a squared minus, I'm going to subtract b squared, apologize, okay, and it's going to be ab minus, ab minus b squared, okay? So I did this earlier, so I wanted to mess it up. All right, so there, that's mathematically correct. Now we're going to factor this out, so we have a plus b minus, no, times, excuse me, a, I use small a's in one p, minus b, that's going to equal, we factor this out, as b times a minus b. Okay? So, now we reduce this out, right? And we just divide this, we're going to divide this out by a minus b, right? A minus b. Okay, we're going to have a plus b equals b, right? Okay. So a plus b, we can substitute, would be a plus a equals a, right? Which is the same thing as saying 2a equals a, okay? 1a, right? And we can divide both sides by a, and 2 equals 1. Alright? So, this is what happens when we do these things called mind experiments sometimes. When we start playing with the math before we look at what we're trying to describe. In other words, we write a mathematical formula and it looks cool and you can see all the functions we can do and it's fun and it's exciting. But then we're trying to make some reality fit this formula. We're trying to find a physical similarity between something in the real world and our fantasy mathematics. And obviously 2 does not equal 1. Well, the problem starts coming is when we start taking and we're, I actually wrote this a little bit wrong when I did that. This is supposed to be a minus b. Is when we subtract a squared and b squared, if this is 1 squared minus 1 squared, it equals 0. Okay? And the 1 over here, that would be 1 times 1 minus 1 squared, still equals 0. Alright? When we get to here, a minus b is 0, and a minus b is 0, again, okay? Well, we know that division by 0 is undefined. So, on the surface, it looks like we have some valid argument, but in reality, we have a fallacy. These are called mathematical fallacies, and there's a lot of them out there. They're quite common. So the answer to Catts' question, really, is that the arrangement that's set up, the question being asked, is a question of fallacy. In other words, the situation as Catts described it doesn't really happen the way it's being described. Just as this mathematical formula cannot produce 2 equals 1 because at this point we have 0 and the formula becomes undefined. The rest of the steps are immaterial. They can't happen. The same thing happens with what you see in there in the diagram of Catts, and you can see how the graphic moves. It doesn't really happen that way. Once the wires are connected to the battery, the charge is almost instantaneous. Now, if we have a long enough wire, we could actually connect them on one end and be far enough away to observe a delay if we could see both ends at the same time. If we had a long enough piece of wire that circled the globe and came back around the other side, we could connect it at a distance and there'd be a slight delay before the light came on. We could probably sense that with our naked eye. However, in reality, what we can say is this is instantaneous. Now, if the light bulb is the last thing connected, or the resistor, then obviously both wires before you ever got down there are at that charge. And these fields don't happen the way it's being shown there because both charges are going out. The negative and the positive charge go out at the same rate. The bottom wire becomes negatively charged just as fast as the top wire becomes positively charged if both wires are connected at the same time. Okay? If they're not, well then that's a different problem. So anyway, what we're trying to show is that there's a direct correlation between using things, sciences like hydrodynamics and pneumatics to demonstrate the principles of what we're seeing in electronics. And when you can physically see something happening, it's a lot easier to be able to explain the unseen. We can't see the electricity flow. We don't have the sensor apparatus in our bodies to physically see that electrical flow more than we can see light from the side. We can't see that, but we can demonstrate what's going on using other analogies. Now, in one of our next videos, what we're going to talk about is how this battery here that we show here in the diagram, how that battery can actually come about to begin with. You know, what causes the electricity to flow? That's the real question. It's not the types of questions that Cat put on the board here, that Cat drew up years ago, and they were good mind joggers. However, they're an engineering fallacy. It doesn't really happen that way. Physically, it doesn't take place the way the problem describes it taking place. So what we'll be able to do is when we look at one of the possible explanations of how a battery works is we'll be able to understand how we can relate the forces of electricity to that of pressure and fluid dynamics. And once we can do that, we can see how and why electricity starts to flow and what makes a battery work. So that will be an interesting discussion that we'll have, and I look forward to bringing that to you. Thank you for participating in this. And like I say, the real answer to Cat's question is the problem is a logical fallacy. It's an engineering fallacy. You can't actually create in the real world a problem as he described it. Similar but not the same, and it's that little difference that makes it an easy explanation to understand. Thank you for joining us. We'll see you.